Welcome back to the Explainer. Today, we are going after the absolute holy grail of modern parallel computing, taking Rust's legendary fearless concurrency and bringing it straight into the beating heart of graphics processing units. Now, if you've ever dealt with GPU acceleration, you know that keeping thousands of threads perfectly synchronized while maxing out performance is, frankly, one of the hardest balancing acts in computer science. Well, today, we're unpacking some truly fascinating research that might have just cracked the code.
So it all comes down to this massive fundamental tension in modern AI infrastructure. The big question is, can custom GPU kernels ever truly be safe without sacrificing their blistering speed? Right now, AI workloads demand ridiculous amounts of parallel compute. But to actually get that speed, developers are usually forced to write custom device kernels that completely throw away the rigid safety nets that systems languages like Rust are built to provide. We all want the safety, right? But we absolutely cannot afford to lose the speed.
Think about it like this, because the contrast is pretty stark. You write CPU code in Rust, and you get perfect memory safety. You get that fearless concurrency. The compiler basically holds your hand and guarantees you won't have data races. But the second you cross over to the GPU, man, it is the Wild West. GPU kernels execute in a single program multiple data fashion. You've got thousands of threads hitting the exact same entry point, and they're only differentiated by a tiny coordinate. In that kind of chaotic environment, correct synchronization and preventing data races, that's entirely dumped right into your lap as the programmer.
Okay, so here's our roadmap for this explainer. We'll start with the GPU's safety problem, introduce Qtile Rust, check out how partitioning divides the work, how tokens order the operations, look at the ultimate performance proof, and finally dive into real-world AI inference. Let's get right into it.
First up, the GPU safety problem, or as it's better known, the Wild West of thread blocks. You see, when your data crosses that host-to-device boundary from your CPU to your GPU, all your beautiful, strongly typed values just collapse into raw pointers. Your safety guarantees practically vanish the exact second the GPU takes the wheel. That brings us to part 2. Introducing Quaddle Rust, which is all about extending Rust's ownership directly to GPUs. This is a newly engineered programming model built specifically to bridge that sketchy host-device boundary. It elevates the programming model to a tile-level abstraction. So instead of micromanaging every single thread, you write sequential code over multidimensional tiles. The compiler takes over, maps those tile operations to thread blocks, and totally handles the complex shared memory behind the scenes.
Moving on to part 3, partitioning, dividing the work to achieve macro-level safety on the grid. So how does Qtile Rust actually pull off this memory safety without killing our performance? It attacks the problem from 2 angles, starting with this brilliant concept called partitioning.
Let's define our terms here real quick. A tile is just an immutable, array-like value of a fixed size. Pretty simple. But a partition, that's the act of splitting up mutable data, say a giant output tensor, into entirely disjoint, non-overlapping pieces before the GPU even launches its work. Imagine it like giving every single GPU worker thread its own exclusive fenced-off desk. Because the launch interface validates this grid before the code even runs, it structurally guarantees that no 2 threads can ever accidentally write to the exact same memory space.
This is so cool because it perfectly translates Rust's famous rule of aliasing exclusive or mutability straight to the GPU. Basically, if a tensor is mutable, meaning we need to write to it, it becomes an exclusive disjoint partition. Every single tile program gets exactly one destination to write to. But on the flip side, if a tensor is shared and read-only, it's just broadcast out to all the programs, and the compiler can freely reorder operations to max out our speed. By forcing all writes into these strict partitions, an entire class of bugs, like data races for messing up an index, are literally impossible to write. There's just no custom index for you to mess up.
All right, part 4, tokens, ordering the operations for micro-level safety within the thread. Okay, so we've separated the threads from each other, but what about the actual sequence of operations happening inside a single tile program? That's where Qtile Rust introduces tokens.
You know, compilers absolutely love to reorder our operations behind our backs just to squeeze out a tiny bit more memory throughput, right? But if a compiler reorders a read and a write on the same mutable tensor, you completely destroy your data. To stop that, Qtile Rust threads these invisible tokens through your mutable code. It's kind of like an unskippable checklist. For instance, step 1, a load operation, has to consume an initial token, let's call it T0, and that produces token 1. Then step 2, a store operation, literally cannot execute until it consumes token 1, which then produces token 2. This strict happens before sequence totally blocks the compiler from dangerously reordering memory on mutable data. But it leaves your read-only operations totally unconstrained, so they run as fast as the hardware allows. Which brings us to part 5, the performance proof. And honestly, this is the elephant in the room. Does all this safety make it slow? I mean, this sounds incredibly rigorous, but we all know developers only run to the GPU for one reason: raw speed. So, does wrapping our kernels up in strict memory safety, partition checks, and token chains just totally tank our performance?
Well, here is the moment of truth. When running compute-heavy matrix multiply operations on huge data center-grade NVIDIA B200 GPUs, safe cuddle-tile Rust performs right alongside completely unsafe raw pointers. The performance is literally neck and neck. The safe tensor API stays completely within the measurement noise of unsafe Rust. So what does that mean? It proves that all of these incredible safety guarantees impose virtually zero runtime overhead.
And the ultimate result is this massive, jaw-dropping number: 96%. Not only does Qtile Rust match unsafe code, but it actually reaches 96% of the absolute peak performance achieved by NVIDIA's own highly optimized vendor-provided QBlast library. We're talking about hitting over 2 petaflops per second, all while the compiler is completely guarding you against data races. It is just a stunning validation of this whole architecture. Finally, part 6, real-world AI inference, featuring the Grout inference engine. Let's see how this tech actually holds up outside of perfect little micro benchmarks and in the messy real world. To test this, researchers built Grout, which is an end-to-end AI inference engine for the QN3 large language model, and it's built squarely on top of Qtile Rust.
And wouldn't you know it, Grout goes toe-to-toe with established, state-of-the-art inference engines like VLM and SGLang. Running a 4 billion parameter model on a consumer RTX 5090, Grout actually pushes the highest decode throughput out of the bunch, hitting an impressive 171 tokens per second. It really just proves that if you keep a lean runtime and fuse operations properly, a totally memory-safe Rust framework can easily compete with heavily entrenched, highly optimized ecosystem players.
So let's wrap this up with a massive question. What does the future of AI infrastructure actually look like, now that the fearless concurrency barrier has finally been broken on the GPU? I mean, for years, developers had to make a painful choice between the safety of a modern compiler and the raw, unbounded throughput of a GPU. But with elegant solutions like compile-time tensor partitioning and token-ordered operations, Qtile Rust is proving we can actually have both. As our AI models just keep growing larger and our systems get infinitely more complex, building on a perfectly memory-safe foundation might just be the secret key to unlocking the next decade of performance. Thank you so much for joining me today to unpack this fascinating architecture, and I will catch you in the next explainer.